That you guys are having a good start to your day. So, good morning, everybody. It is 9 a.m., so I'm going to go ahead and get started. What we're going to be talking about today is, well, I hope that you guys had the opportunity or took the opportunity to read my note. Friday's class will be an asynchronous meeting, so I'll be posting the link for that pre-recorded lecture before 9 a.m. on Friday. I'll hope to get it up soon, but I just want you to know it will be available to you before your class. There won't be any top hat questions today, nor will there be any top hat questions on Friday. But I will put some quizzes up so that you guys have some kind of questions and where do I go with this information? So, with that in mind, what we're going to do today is we're going to talk about enzymes and we're going to kind of continue our conversation about enzymes. Now, if you remember what we've talked about so far with respect to enzymes is kind of we've talked about coenzymes, we've talked about cofactors, and we've talked about prosthetic groups. Today, we're going to get into what I think is a little bit more of a tangible conversation, I guess you could say, something that makes enzymes hopefully a little bit more tangible, in terms of what they are and kind of what we're looking at. So when we talk about enzymes, well, we're going to talk about a couple of the different things. Today, what our focus is going to be on is a little bit more of this item right here, binding patterns. Enzyme classes, that's something that I want you to know about, and that is what we've previously talked about, your lyases, ligases, oxidoreductases, hydrolases, transferases, and last but not least, lyases, ligases, isomerases. Okay, so those are our six major ones, and that seventh one, if you're preparing for the MCAT or doing some standardized exam, would be your translocases. Um, Now, with that in mind, let's talk about an enzyme. Now, what I think is important to know is that most often when someone's talking about an enzyme, they are talking about a molecule that is a protein. So something that's made up of amino acids. Now, that's a very important distinction. So I'll add this item right here. Not all enzymes are proteins. And this is a distinction that's important to note because there's something known as your ribozyme. Oh, ribozyme, which is a RNA molecule that has catalytic activity. So an enzyme is effectively a biological molecule. You got to take a little bit of a broader perspective on this, that it's a biological molecule that catalyzes a particular activity. Now, despite this, more times than not, when people are talking about an enzyme, they are talking about something that is made up of amino acids. So this is an item that is important to know, um, an important distinction, just so you have a comprehensive view of what an enzyme is. But for most purposes, when somebody's talking about an enzyme, they are talking about a protein or a polypeptide, something made up of amino acids. Now, this right here, this whole molecule here, is the enzyme known as lysozyme. Now, lysozyme is a specific enzyme, and what it does is it cuts polysaccharides of bacterial cell walls. So it takes these long polysaccharides. So if I could draw a very, very crude one right here, there we go. Yeah. Square, 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 square. And it breaks the glycosidic linkage between those. This whole molecule that's in white, red, and blue, that is an image of lysozyme. Now, there are different regions that are highlighted because they have a particular function and they have a particular role in the function of lysozyme. Before I show you that, though, this black molecule that's in the middle, would anyone care to add to the chat what they think that is? And I'll give you a little bit of a spoiler. It is not the enzyme. It's the substrate. Absolutely, Morgan. And so that is the substrate. That is the molecule that our lysozyme acts on. Now, a little bit more specific, it is our polysaccharide. And we're going to get into a little bit later on the mechanism by which lysozyme functions. So we'll look at where that polysaccharide is cut. But for our purposes now, well, that's the sugar. That's the long polysaccharide that gets diced up by lysozyme. So there's our substrate. Then I need to erase some of my writing down there. That blue region is the substrate binding site. So that's basically where the substrate is going to kind of be attracted to on the structure of lysozyme. And the red region, the red highlighted region, is your active site. Now, this model that is shown here of lysozyme, this is known as a space filling model. And I think that there's another more specific name for this kind of brand or this type of space filling model, and it gives the it's coming from the electron density of all the amino acids that make this up. What I want you to know about this is lysozyme, if I remember correctly, is a singular polypeptide. So this is looking at the tertiary structure of lysozyme. And I'll give you a good resource. Anytime you're curious about a protein structure, there's something known as the PDB or the Protein Data Bank. And basically, any known protein structure, whenever it's solved, it's deposited at the Protein Data Bank. And so this is just an example of a model for lysozyme. Now, all of these kind of like grooves and everything, all of these spaces that are kind of protruding out and all this three-dimensional modeling, well, those are amino acids. Now, when you think about any enzymatic reaction, there's a couple of things that you have to keep in mind. What do you need? Well, one thing that you're always going to need is your enzyme. In some instances, you might have two different substrates. Now, in the case of lysozyme, lysozyme has one substrate. There are many enzymes that have two substrates, and these are known as bi-substrate enzymes. And bi-substrate enzymes catalyze, well, you guessed it, bi-substrate reactions. Now, in an enzyme reaction, what's going to have to take place is both of those substrates are going to bind. If I had to guess, there's probably someone in here who's looking at it and they're like, well, if we toggle back and forth, this slide to this slide, well, that looks almost like both A and B. I'm not seeing a step, I'm not seeing a progression other than they both bind simultaneously. And a very fair question that somebody probably is curious about is, well, is that how it works? Do enzymes bind two substrates at the exact same time? Or, is an enzyme going to bind A and then bind B or bind B and then bind A? And that's a fantastic question because it's variable. And we're going to get into modeling that and looking at what that looks like in just a little while. But for right now, let's look at this as, well, you have your two substrates bound, and this makes up what is commonly known as the ES complex. We'll refer to Cleland, Cleland notation. And Cleland notation uses E for enzyme S for substrate, typically P for product, just to keep it as simple as possible. Now, when there's multiple substrates, that Cleveland notation might change a little bit. You might say E and then A and B, and then P and Q are your two products. It's a little bit variable, but Cleveland notation generally follows the rule of single letter, single capital letter indicates, well, your enzyme and or your substrate. Now, whenever both substrates are bound, well, the enzyme is going to cause those substrates to basically come in close enough proximity to one another, and you're going to see a catalytic mechanism, much like the mechanisms that you saw in organic chemistry too, where you're pushing electrons around. Well, in this case, it's the amino acid side chains that are the agents of moving those electrons around, that are there to establish a bond or to break a bond. And whenever that's taking place, we qualify and we make a small adjustment. We add a star. That indicates that our reaction is actually taking place. So that ES star indicates the reaction is, sorry about that, taking place. Now, that phrase right there, taking place, makes it sound like it, endures for a long time. That's not really the case. It happens very rapidly. But that star is what indicates we don't just have those substrates bound, but instead the reaction's actually ongoing. Now, substrates are going to affect enzymes on binding because what's going to happen is we're going to have, well, here what we have is our two different substrates, A and B. Well, parts of those change. So A is kind of a thing of the past. Likewise, B is a thing of the past. A has changed. That substrate, after a reaction has taken place, has changed. And so we're going to use a different letter to denote that. And again, with this Cleveland notation, P or Q, B or C, it's not of the utmost importance that we kind of hold a hard line. I would say that E is pretty consistent for a enzyme and A for a substrate, but and then P for product, but there's, creative liberties you can have with this. So part of A is removed. See this kind of magenta ball in the foreground? Well, it moves from, I'm going to go back. It was initially on substrate A, and now it's moved over to substrate B. So A is without that magenta ball and is therefore substrate, or it's known as your product C. B kind of receives that magenta ball. And these are simply models to show what's going on here. But it's always helpful or it might be helpful for you to think about, well, what is that magenta ball? Let's just think about it as a methyl group. So we have a methyl group that's moved from substrate A, and now substrate B results. And if you're thinking, well, what's a methyl group? Well, one example, or not what's a methyl group, if you're thinking like, well, I need an example, there is a molecule that maybe you've actually seen at like HEB or something like that, SAM. And sometimes you might see it as all capital S, capital A, capital M, and then a lowercase e. And that is a molecule that's commonly a methyl donor in a biological system, and it's known as S-adenosyl methionine. Okay, now as we proceed, so A has become C here, B has become D here. Now, this is where both the products are still bound to our enzyme, and we get the EP complex. Well, our products are bound to that enzyme. Now, what's ultimately going to happen is, well, your enzyme doesn't really want to hang on to those products. Those products need to be released so that they can go on to do whatever they need to do elsewhere in that biological system. And that's where we get E plus P. So it's important to recognize that there is kind of a progression of what's taking place here. We have a total of 5 steps typically. You have the free enzyme. The free enzyme is denoted by E, and that free enzyme is present prior to the binding of the substrate and after the release of our products. We also have S, free S. That is your substrate. That is your substrate that has not bound to the enzyme. Well, when that binds to the enzyme, we get the ES complex. Then we get ES star, where our reaction has either taken place or is, kind of going to commence. Then we have EP, where our product is actually generated. And then we've got E plus P, where our product has been generated, but now it's been released. So there are a couple of things that are really important to keep track of. Anytime I mention or anytime you hear about free enzyme, well, think about what that free enzyme is capable of doing. Well, that free enzyme, or kind of where it is in the system, that free enzyme circles back and can bind the substrate again. This kind of chronicles or punctuates one of the important parts about any enzyme catalyzed reaction. The benefits of a biological catalyst and an enzyme catalyzed reaction is that biological catalyst is ready to go again. Well, it's produce the product, round two, produce the product, round three, produce the product, round four, and it just keeps going and going and going because that enzyme, all it needs to have are the two substrates or the single substrate, whatever that may be, and it can carry out its reaction over and over and over again. So when you hear free enzyme, I want you to think about, okay, that can either bind to the substrates or, so maybe I'll change that to, and or it has just released products. Um, with that in mind, there are some instances, specifically with oxidoreductases, where an enzyme is a part of a complex, and an enzyme might have to have some sort of oxidation reduction reaction take place because maybe it's undergone a change during that reaction. But just think about this as, well, that free enzyme is basically ready to go for rounds 2 and 3 and 4 and so on. Now, next up, this ES complex. Well, that is where our enzyme is bound to our substrate, and then EP is where our enzyme is bound to our product. Those two structures or those two complexes exist. Now, it's pretty common to see a simplified version of this that looks like this. E plus S yields ES and then E plus P. Now, I think that it's common to see this or these kind of 5 steps simplified down to a total of, well, basically 2 steps, step 1, step 2. And the reason for that is this combo, actually, I'll make it, oh, darn it. Let me make a little change to that. All 3 of these, that's effectively what exists right there. The enzyme binds the substrate very rapidly, produces the product, and then releases that product. So when you see notation like this, you could think about it applied to this as, well, your enzyme substrate complex catalyzes the reaction, releases the product very rapidly. Now, that's one important thing to recognize about the 2 different notations that you might see and kind of reconciling them and understanding them. Now, as we proceed, there's a number of different types of reactions. I've already shown you a model that would be a bi-substrate or a double or a 2 substrate reaction. There are also single substrate reactions where, well, a single reactant is converted to a product. And it's converted to one single product. There are single substrate multiple product reactions where effectively, a good example of this might be something akin to like an aldolase, where we take a 6 carbon sugar and split it into two 3 carbon sugars. So a single substrate is brought in and two products are released. Multiple substrates might be combined to make a single product, or we can have these bisubstrate or multi-substrate, multi-product reactions. Now, when it comes to these multi-substrate, multi-product reactions, they kind of get a little bit hairy because there are a couple of different, like the sequences and the patterns in which the binding takes place are a little bit variable. And that's where we have different terms. We have an ordered, a random, and a ping pong reaction. Okay, so we're going to get into the ordered, random, and ping pong reactions in just a little while. But before I do that, I want to talk to you about, well, let's make it kind of as kind of simple as possible. And let's get our fundamentals all shored up. So we have right here that simplified model where the enzyme binds to the substrate, forms the ES complex, forms the product, releases that product, and then reforms the free enzyme. Okay. Now, when we think about basically affinities and binding between your enzyme and your substrate, there's a couple of things that can happen. When the enzyme and the substrate come in contact with one another, that enzyme substrate complex is likely to form. So let's go with scenario one. One. Substrate is ultimately converted to the product, and the free enzyme does this and is returned to the free enzyme. Okay, that's one possible outcome. Scenario two. So actually, let me add one little addendum to this scenario one, and that is where effectively we can say move all the way through to the right. Okay, scenario two. In scenario two, well, what can happen is the enzyme and the substrate might come in contact with one another, and they'll lead to the enzyme substrate complex. But maybe the conditions aren't perfect, or maybe the conditions not perfect, but aren't optimal, in which case that enzyme substrate complex returns to the free enzyme and the free substrate. So effectively, ES breaks down. And you could simply put it as no product is generated. Okay. Now, scenario three, and I'm going to go ahead and use my pen to highlight basically scenario one is represented by that line and that line. And then I'll change color to green, and I'll say this represents scenario two. Okay. Now, the least likely scenario, but I'll bring it up, is scenario three. And scenario three is where E plus S forms ES, and then P plus E are formed. Now, this is where we move all the way to the right, but why I highlight this one is because, well, in theory, in order for a enzyme substrate reaction to be produced, or sorry, an enzyme substrate complex be produced, the product in the enzyme could go back. Basically, the reaction could be undone and that ES complex is formed. And then if that ES complex is formed, well, then the free enzyme and the free substrate complex are formed. Now, I'm not going to use a color to indicate that. And the reason is because if you look at this right here, and let me go ahead and actually erase, boom. I'll highlight it again though. Notice the arrows. It's not an equilibrium arrow. And the reason is because effectively, um, Morgan, thanks for the question. I'm going to, sorry, I overlooked your question. I'm going to post them on Canvas a little bit later today. Sorry about that. Um, and sorry for the delay on me noticing that. Effectively, the product in the enzyme, the P plus E, is in such an unfavorable equilibrium with the ES complex that it's almost like if you think about the magnitude of a equilibrium constant, the magnitude of this equilibrium constant favors P plus E so much that it's kind of a fool's errand and just not even worth it to draw this reverse arrow because that reverse arrow is basically not going to take place. So that's why we have equilibrium arrows to represent K sub 1, the forward reaction and the formation of the ES complex, and then K sub minus 1 to represent the dissolution of the ES complex, and then K sub 2 to show the ES complex going towards the P plus E, but not going backwards. We don't have a K sub minus 2 because the equilibrium just does not favor that at all. Now, in the event that you see this, if you ever see K sub minus 2, is that wrong? No. Is what I've got represented here wrong? No. It's just for all practical matters, that reverse reaction is basically not going to happen. Now, when it comes to enzyme kinetics, so here's our kind of binding scenarios. When it comes to enzyme kinetics, what we're most interested in when it comes to enzymes is we're interested in the V sub 0 or the initial velocity. Now that V sub 0 is the kind of I always think about it as like, or I always like to think about it as similar to when you're doing a sprint. If you're sprinting, 50 meters or something like that, or 100 meters, well, presumably the fastest moment is going to be when you're on those starting blocks and you initially push off. So that's your initial velocity. That's going to be where you're the fastest. And let's just imagine someone who's not particularly well trained for that distance. I'll use myself as an example. I'm not a 100-meter specialist by any stretch of the imagination. I'm going to be fastest whenever I come out of the starting position. As that race continues, I'm going to get a little bit slower. And so meter 10, 20, 30, what's going to happen is the velocity that I'm bringing to the party is just going to diminish. It's going to decline over and over and over again. Now, enzymes kind of are the same way, which is why we're most interested in that initial velocity. So that's what we're always going to plot. Now, when it comes to looking at an enzyme's kind of overall performance, what we want to do is we want to track this by giving your enzyme different concentrations of the substrate. So I'm going to go ahead and put together a series of trials. So let's see, we've got T1, T2, T3, T4. Now, these are experimental trials where I'm not going to vary the amount or the concentration of my enzyme. What I am going to vary is my substrate concentration. And so that is my first column. And then my second column here is going to be my rate. Now, typically, whenever you look at an initial velocity, Effectively, what this is concentration of your product, because that's kind of what an enzyme is looking to do. It's looking to make a product. Your concentration of your product over time. So when it comes to like specific units, it's pretty common to see something like, let's say, nanomolar per second. And sometimes you'll see that written as NM SEC to the negative first, nanomolars per second or nanomolar per second. Now, with that in mind, here's our substrate concentration. And let's go for trial number one. I'm going to use um, one, and I'm going to go ahead and use millimolar as my substrate concentration. I'll go with 1, 2, 4, 8, and then let's just go with T5. Let's go with 10. Okay, so I'm gradually increasing my my substrate concentration in every successive trial. And so what I'm going to get is 1, 2, 4, 8, and 10. Now, I haven't scaled that particularly well, but here we go. Let's say that your initial velocity is, let's go with 0.5, and then 0.9, and then 1.6, 1.65, 1.66. Okay. Now, what I want somebody to add to the chat is, what do you notice about, let's say, trials 1, 2, and 3 and their velocity? And you could look at that as, well, from trial 1, it's this, to trial 3, it's this. What's kind of a trend that you notice about those numbers and how they increase? I mean, first of all, the numbers do increase. There's no doubt about that. 0.5 to 0.9, that's nearly doubling. Okay, I like it. It's close to, that's good. Those are perfect contributions. So if we were to plot this, I think that we'd see something, and of course, I don't have this on my y-axis, but does anyone object to that plotting without the y-axis, shown there? Let's go ahead and I'll put that in though. 1, and then let's go with 2, or yeah, I'll go with 1.5 here, and then 2 here. Yeah, I feel pretty good about that plot. It goes up pretty rapidly. Now then let's look at when my concentration is 8 millimolar for my substrate. Then what I see is kind of goes like this. And then when it's 10, I see it goes from 1.6 to 1.65. Lena, absolutely perfect. Okay, Lena. Now, looking at that graph and the way that that data displays, does that resemble any plot that you've seen before? Milo, absolutely right. It looks like an oxygen binding curve for myoglobin. Because, and I'm happy, had you just said oxygen binding curve, fine, but you specified for myoglobin. You're absolutely right. Because what we're seeing is that at some point, effectively the concentration of our substrate, if you can imagine, and I'm going to add like a 12 and 14, 1, 4. You can imagine that, well, that data kind of flattens out because we see this trend, and we haven't done this, and this is an imaginary hypothetical enzyme that I'm describing, but it seems like the increase in concentration isn't changing the rate for those last, 2, 3 data points. And that's significant because effectively what that's saying is you kind of reached a capacity of that enzyme. Because if all in all of these trials our enzyme concentration is held even, then we have pretty good reason to believe that, well, the only thing that we could change to get a higher velocity and more generation of our product would be to add more enzyme. But that's not what we're looking at. We're trying to understand this particular enzyme. And so if we were to draw this out, we'd see it probably look a little bit like this, where it kind of plateaus. Now, that's significant because that tells us that we're looking at, well, an enzyme that is the limiting factor because we've effectively saturated our enzyme with the substrate and we see the velocity kind of plateau. Now, with that in mind, well, a good question I think to ask is if we think about a oxygen binding curve for myoglobin, I'm going to draw a quick one right here. We had this right here. Does anyone remember what that y-axis related parameter was? It's our basically our 100% saturation. Yeah, absolutely, Milo. Now, with that in mind, did we use that to come up with an important parameter for oxygen binding proteins? Give you I was going to give you a hint. Absolutely, the P50. And we use that P50 because we said, okay, well, half of the capacity, and then we look at the concentration of our O2, or our partial pressure of O2 gets us here. Let's say that's 5, just a random number there. Then you could say, well, the P50 of this protein is 5. Okay, great. Now, looking at this curve right here, the one on the left, this is a enzyme kinetics graph. And effectively, you know, we've got a similar shape and we've got similar kinds of parameters. We've got a level of saturation where, yeah, you can add more and more and more substrate, but it's not going to matter because as you add more substrate, well, the enzyme can't get any faster. It can't catalyze the reaction any faster. And so we do kind of the same thing. We look at parameter right here. And we refer to this as the V max, the maximum velocity that the enzyme can catalyze the reaction. So V max is one important kinetic parameter. V max is basically, I always kind of think about it as fast as you can go. And so as fast as you can go, let's go ahead and say that this is, I don't know, let's call it 1.70. And then our product might be nanomolar per second. And just as a little bit of an aside, I use millimolar for my substrate concentration, and I used nanomolar in my velocity. Was that intentional? It was. It was because of the fact that you might be loading up your substrate at, a molar concentration, but your product might not be generated to that degree. So if ever you see, oh, millimolar and nanomolar, those have to be the same. They don't, because you're looking at the input of the reactant and the output of the product. You're measuring different things. So their magnitudes might be different a little bit. So, nanomolar to millimolar, that's like a 1,000 fold difference. Is that something that's, I'm sorry, reasonable? Yeah, it's possible. So, at any rate, we've got our maximum velocity, and that is a velocity, or our Vmax. So our units are going to be a concentration or amount per time interval. Now, We also have something similar to this in terms of being analogous to, or we have another kinetic parameter known as a Km. The Km is similar to the P50 in the sense that the way that you calculate it is by taking your y-axis and base your y-axis and looking at that maximum velocity and more or less cutting it in half and saying, okay, well, right here is my half of my Vmax. Now I'm going to play a little game of Battleship and align that to my x-axis. And I'm going to make an approximation here. Of course, these are, hand drawn, but whenever you plot these data in something like Sigma plot or Excel or something like that, you're going to get a little bit more precise of a measurement. And let's say that this is, 1.7 millimolar. That is the concentration of our substrate that gets us to half of our maximum velocity. So substrate concentration that gets us GETS or gets our enzyme to half of its maximum velocity. Okay, so these are important kinetic parameters. Now, that first item there of Km, substrate concentration, let me ask you this. Do you think that a Km has units? Yes or no? Okay, yes. What do you think those units might be? In this particular example, what do you think the units would be? Well, in this case, what we can do is we can look at, well, what were the units of our substrate? Our substrate units were millimolar. And so as a result, in this particular example, well, our units for Km would be millimolar. Are Km always going to be millimolar? No, not at all. Km might be nanomolar. It really depends on, well, what are the units of that x-axis? So I bring these 2 points up and I'm stressing units because of the fact that this is something that people have a tendency get mixed up on. They think about, well, Km is half of the maximum velocity. Okay, no, it's the substrate concentration at half of the enzyme's maximum velocity. So it does have units because Km is a measure of, well, the concentration that kind of attains that. Vmax, maximum velocity. I always think about a car. What's the max or top speed in a car? Well, it might be 120 miles per hour. It's a distance or it's a unit per unit time. In this case, we're talking about generating a product. So how do we measure products? Well, we look at concentration of them. You might also sometimes see this as like, um, excuse me, I apologize, milligrams per minute. You might see something like that. Maximum velocity, importantly, is a quantity. That might be a concentration. It might simply be an amount per unit time. Okay, so these graphs are extremely important for you to understand. Or sorry, not these graphs, but this graph on the left-hand side here um, is an important one to understand. And the last point I want to stress about this graph is that when you see this graph, or the next time you see one of these graphs, what you'll see is something that looks like this. Okay. One thing that I have had people get mixed up on is, and they kind of lose sight of, well, the curve of this graph here on the right-hand side, the curve and the shape of that graph is only because of That's what the data says. We did, you know, 125 trials of this enzyme, increasing the substrate concentration. And we saw that at this substrate concentration, the enzyme's maximum velocity plateaus. It no longer increases. So all of those dots, I'm drawing all of those dots there to indicate that would be trial number 42, just as a number, just to kind of illustrate that point. Because I think that what I've noticed over the years is that people look at that curve and they think of, okay, well, experimentally, like I'm doing this experiment, I added my enzyme and then I just threw a little bit of the substrate in there. Good. And it's not quite that simple. Now, what we can do with this is we can come up with a really nice equation that explains that graph. That equation is known as the Michaelis-Menten equation. And this is a really awesome equation to know because it's named after two people. And one, I think they were at McGill University in Canada, I believe. Um, I always like to bring up Maud Menton, in part because, well, Maud Menton was a woman back in the late 1800s, early 1900s, I believe, was whenever she had her scientific career. And it's not every day that you hear about a woman biochemist more than 100 years ago. And so I think that it's pretty great to highlight those examples. So Maud Minton and I believe I cannot remember what Michaelis's first name was. Um, at any rate, they derived this equation. They developed this equation, and they based it on experiments with different enzymes. And they said when the enzyme is saturated, the velocity is going to be at its max, which is shortened as your Vmax. When the substrate concentration is very high, okay, this is kind of one of the assumptions or an important part to recognize about this. When the substrate concentration is very high relative to your Km, all of the sites that that enzyme can bind to are going to be occupied. So effectively, your enzyme concentration at that time is equivalent to or equal to your enzyme substrate complex. So in another way of looking at that, you could say that your maximum velocity is equal to the rate constant, your K2, for the conversion of the enzyme substrate complex, or K2 times your enzyme concentration at a given time. Because whenever your substrate concentration is very high, E sub T is equal to ES. Now, the enzyme is not always saturated, so velocity at all ranges of substrate concentration is given by the Michaelis-Menten equation. And that equation looks like this. Here what we have is Vmax over V sub 0. In many cases, what you'll see is you'll simply, no, that's not right. Um, sorry, let me do one thing. My lines got a little bit distorted there, so let me fix this. This is always annoying when that happens. Let me go to a previous slide because then I can make my edit and then bring it back. Just like that. There we go. So your Vmax, or your maximum velocity, is equal to your substrate concentration times initial velocity divided by Km plus substrate concentration. That's okay. So what we can do with this equation is basically come up with the Michaelis-Menten plot, which is basically what we drew right here. So this graph right here is your Michaelis-Menten plot. This one on the, well, actually, both of these plots are your Michaelis-Menten plot. Now, that is a non-linear plot, and so it makes it a little bit difficult to make an approximation of what your Vmax is. So what we can do with that is we can rearrange the components of that plot and come up with a Lineweaver-Burk double reciprocal plot. Now, what we're going to do is I'm going to give you I think that I've got a data set that I can provide you with where you'll take V sub zero data and substrate concentration data and take the reciprocals of both of those. So all that you are doing is taking a data set that's V sub zero, T1, T2, T3, and so on, and then substrate concentration. And you're going to more or less convert that to 1 over V sub zero and 1 over substrate concentration. So effectively, let's say our V sub zero is 3. We're almost done. Well, you know what? I'm going to go ahead and stop right here. Um, sorry, I don't want to try to rush this. Um, but I'm going to be uploading. I think what I'll do is I'll upload through this slide right here to our Canvas page. And then I have to, I'm sorry, but I got to look at that Michaelis-Menten equation. I think my formatting got all screwed up there, so I apologize for that. I'm going to fix that, and then that will be your PowerPoint for Friday, which again will be a pre-recorded lecture. And yeah, well, thank you very much for coming to class. I hope you guys have a great day, and I hope that you have a great week and a great weekend. Thank you for everything, everyone. Bye.